Welcome to Chapter 2. In this chapter, we're going to talk about database design fundamentals. A little bit of a side note here. This chapter tends to be the most complicated chapter for students. In fact, this week is just a tough week in this class. So please make sure you're giving yourself plenty of time to work through these options, through the homework, through the chapter. Make sure you read the chapter. I find that most students tell me that reading it a second time makes things better. So give yourself plenty of time to do that. We're going to jump in and talk a little bit about what it means to design and create databases. In this, we're going to talk about some terms you need to know. We're going to talk about entity, attributes, and relationships. Under these, and then with a relational database, the biggest piece you got to understand is that there's relationships between the relational database or relations, right? Understand fundamental dependencies and how to identify those. We're going to talk about primary keys and how to identify primary keys. We're going to talk about requirements when it comes to a database and how to design a database. A little side note on this is one of those things that I see often with students. Because this class is about designing and developing, I take a very strong approach to to requirement gathering and following the requirements. What I tend to find is students will oftentimes give me something other than what's been asked of, or they give me more than what was required. I will take points off in homework when that happens because it's important to understand that requirements are the contract between the developer and the client. It's the set of requirements that needs to be satisfied. And believe it or not, at times giving too much or giving more than the requirements is also problematic. So we're going to definitely focus on making sure we satisfy the requirements, no more, no less. All right. Convert an unnormalized relationship to first normal form. Then we're going to take that first normal form and go to second normal form. And then finally, we're going to talk about third normal form. With that, we're going to create an entity relationship diagram to represent the design of a database. Entity relationship diagram, also known as ERD. So let's get into that. All right, so when we're talking about database design, the process of determining particular tables and columns that will compromise a database, you've got to get used to figuring out when you're reading requirements, what are the tables that we're talking about? And we got to understand database concepts to do that. And we definitely have to know the process of normalization. Now, normalization in theory is now more troublesome to learn than I believe it used to be. And the reason being is now as people, we are always using things like Excel and other products that we oftentimes now think of data in with a normalized process already done. We don't tend to think of data outside of normalization. So what you may find when you're doing this is you may actually find now it harder to represent data doesn't have some form of normalization to it. You are going to probably second guess yourself. That's what I have seen. And even when I teach this course now, it's tough for me to think and show actual representation of unnormalized data. So kind of keep that in mind as we go through. We'll do our best, and when you feel like you've got data that doesn't look right, more than likely you have an unnormalized data. So some database concepts. Let's talk about entities. So what is an entity? Well, an entity is really any piece of information that you want to gather data on. Let's talk about a couple of different entities. You might be talking about, let's build a database around a car. Well, a car is going to have parts. Now, maybe the car itself is an entity. The parts that are going into the car could also be entities. In fact, oftentimes when we're looking at database concepts and design, we notice that the nouns of our requirements oftentimes tell us pretty cleanly what our entities are. So in our car example, like I said, the car itself might be an entity. The steering wheel, which has attributes, which is the next word, by the way, that we're going to talk about. It might be 13 inches in diameter. I just bought a new truck, and the steering wheel is not actually completely round anymore. It actually is a little bit more. It's round, but it's got like this deep impression, so it's not one linear plane anymore. So there's an attribute that could describe that entity, and that's the important thing to understand about attributes: is they are what describes entities. So any entity that has these attributes are oftentimes known as, so an entity is a table, and an attribute oftentimes are columns. And what brings all this together? So let me explain. If you've got a bunch of tables and they don't have any relationship to each other, then you don't really have a database. You just have a bunch of tables. If you decide to go into a database and make one table about the classes you're taking, and then you go in and make another table about your budget, and then you go and make another table about your prized collections, but there's no real relationship, then you just have a bunch of tables. The database doesn't bring it together. Instead, typically, when we make databases, we want relationships, right? So in my example, we could start to make some relationships. We could say maybe my budget table helps me to realize my spend level along with my assets. And some of my assets are maybe these things that I've been collecting, right? They have their items and they have values. And then classes was a table. Well, I tend to have to spend money on tuition. So maybe I add that as part of the classes table, what my tuition is. And I make that as part of my budget. And I even relate that somehow to assets, intangible assets that I have. And I start creating these relationships. Now that database stands for something. It means something. So that's why the relationships is really important. We're going to talk about functional dependencies, and that says that these relationships are dependent on each other. We're going to get a little bit more into that here in a moment, but kind of keep that in mind. And then finally, the primary key. This is pretty important too, because when we talk about primary keys, we need a way to make each row of the data searchable. If you can't search it, if you make it to where all of your tables are, sorry, I'm still learning my tools here. If you make it to where your data isn't searchable, then it's just a bunch of data you can't do anything with. You need to be able to, okay, sorry, I can't still, oh, maybe it's this. There we go. All right. You got to find a way to separate those pieces of data out. So let's take, for example, let's say you have a table of the cars that you own, right? You're rich, you have a bunch of cars, and you want to keep a database or a table of those cars. And let's say you're a real big Honda S2000 fan. And in fact, you've got 3 of them, and all of them are different colors: blue, red, yellow. They all have the same attributes for the most part. And so now you have them in your database. How do you search on one of those S2000s? You can't say, hey, database, show me just one of my S2000s. It's going to say, well, I don't know which one to show you. You need to be a little bit more specific. Which of the 3? Now, I purposely put in there that they all had different colors. So we could search on this by the different colors. But what if we went out and accidentally bought another S2000 of the same color as one of our previous? Let's say now we have two yellow S2000s. Well, now we have a problem. There's no real way for me to, one, search on any of those rows, and two, there's nothing different about those two pieces of row of data. So relatively, even you as a person don't know which one of those rows mean what. So oftentimes we'll use primary keys to help us say this is a piece of unique data. And often those primary keys are used in part of our references that we were just talking about. All right. So in a relational database, we have a collection of tables. We've already talked about the tables in the Tau distributor database. We've got the rep table. We've got the customer table, orders, item. And remember what I was telling you last week? When you have this underscore in between, oftentimes that is to signify that it's the combination of two items together. In fact, oftentimes it will be the actual two items together. So this is a little weird. They didn't really do it like I would expect. So you would see Lord order item. But that's okay. We're going to go ahead and understand that that's what they're trying to do here with this particular underscore. Oop. Still getting used to some of these tools. All right. So we've already talked about an entity. It's like a noun. It's a person, place, thing, or event. An attribute, an adjective, or an adverb, which is the property of the entity. And then the relationship, how we associate those entities together. We have several different types of relationships. And this is probably one of the most common, is the one-to-many relationship. So kind of imagine what you have is you have two tables. In this first table, there will always be only one line of row of data that can reference several rows of data in the other table. So this is known as 1 to n, which means one to many. So you implement by having a column in two or more tables. And so in this case, what we're saying is there's a column in here and a column in here that help reference these tables. Now, so typically, let's say that this is got an ID of 2. Then what this table over here says is that this guy relates back to this table, column 2. Hopefully that makes sense. If not, shoot me a message. I'll try to go over it a little bit more in detail. Actually, let me just do it one more time. Let me try to talk it through just one more time. So again, we've got two tables. And in this particular case, we're going to do a one-to-many relationship. And again, it's this particular case. And let's say we have our ID field, which is we're going to later call primary field. It's an ID of 2, and then there's more data, right? Over in this other table, now remember, this table probably also has its own primary key. So let's just, for the sake of this, say there's 3 rows that we're interested in. They are number 3, 4, 5. There's a bunch of data in each row, but there's also one additional column that says, hey, this all relates back to this table. And we're going to say that this relates, all these rows relate back to the row in this table with the ID of 2. And that's how you get that that's one way of doing a one-to-many relationship. It's one of the most common ways of doing it. So a good example an actual real example is maybe you have a student table, and Mike is ID number 2. And then over here are all the classes and enrollments. And this particular class is SQL. And one of the students is 2, which is Mike. Oh, and then there's a C# class with a student of 2, also Mike. And then we've got, let's say, Java, because, Mike wants to learn multiple languages all at once. So now he's also in that class. So here's an example of, and again, SQL probably has its own ident, let's say 3000. And then C#'s got, maybe 4000. And then Java's, whatever number it came up with, 5001, right? But this 2 right here, these 2s, is what refers back to the student table. Hopefully that makes more sense on that. So when we talk about repeating groups, this is multiple entries in an individual location. So imagine you have one table, we were just talking about that, with all my S2000s. By the way, I've never owned an S2000, but I know it's a popular vehicle among those that like sports cars, so I talk about them. S2000s, this is a repeating group because each time I'm talking about an S2000, this is a group of data. So it's repeating. All right. Let's kind of put some of the things we just talked about together, right? So we talked about an entity. So this is a table. So this itself is an entity. The attributes. Every single one of these columns is an attribute. This data that's in here is actually basically answers to the attributes. So the order number, this is that order number. When it was ordered, the customer number, which by the way is a reference out to the customer table. Here's that item number. And if you'll notice in this table, which by the way, I'm telling you right now, is a table you're needing. This version of this table, you're going to need to understand because of this right here where I'm repeating data. This is that grouped repeating groups that we were talking about back on this table. Let me go back. I'll have to erase all this, but let's go back for a moment. So we were talking about these repeating groups. This is a repeating group. It's 2 item numbers for one item. Same here. We've got 3 repeating groups. It's a repeating group of 3 items referencing one piece. So keep that in mind. Now, we're going to break that out a little bit. Let's go back to what we had here. So we had the KL78 and the TR40 for order number 516010. So here we can see what we've now done is we've taken this data and we've broken it into its own separate rows. Now, how do I search on this data? I can't ask it for just the order item anymore because it's going to not know which row to show you. It would show you both rows, but if you wanted to get very specific, let's say you wanted to edit one of these rows of data, how do I get to this very specific KL78? The way you would do that for this is now you would have to put in your search query both of these pieces. and say, hey, I want to update the table that has both of these pieces of data. And that's how you're actually going to identify that specific row by itself. It's a little bit cumbersome, and we've got better ways of doing it, but kind of understand that that's kind of what's going on here. Is, in fact, you can say that this might be one level of normalization, and this is a little bit better level of normalization. So the reason why I'm pointing these things out, and we're going to get more into detail a little bit, is this particular version of table. It's not normalized. Whereas at least this version, because we've broken out these repeating groups, we've broken them out into their own rows. This is first level. Just understand that for the time being. We're going to get into that a little bit more down the road here, but I wanted to make sure I pointed those out before I went any further. So relationship is a two-dimensional table. And when we say two-dimensional, all we mean is that it's got rows and it's got columns. That's the two-dimensional. So each table, entries in the table are single value. We've kind of looked examples of that already. In this table, you can see that there's only single values per row. Each column has a distinct name. So when we talk about that, we're saying these are all distinct names. All values in a column are values of the same attribute. So again, when we talk about that, we know that this is the order date. We're not going to put, for whatever reason, this piece of information over here. It's always going to be, this is related to that, this is related to that. The order of the columns is immaterial. It doesn't matter. It does not matter if this column was over here and this column was over here. It doesn't matter. It's all the data. It can come in any direction. We can, in our queries, actually say where the data should be. Each row is distinct. Now, this is an important one. This one is important. And we know that because if we come back here, like I said, this row of data isn't actually distinct. I mean, it's distinct, but we could have another row and there's no way to really stop it from being distinct. What I'm saying is when we get over here, because we've now broken these rows out, even though we would need these two pieces to show that row is distinct, it is distinct. No, that's not what I wanted to do. The order of the rows is immaterial. That's the other thing, too, people don't understand. So I want to take this moment just to take a conversation about that. Typically, when we look at data, we will notice that it's in some sort of order, usually based on its primary key. But there's no guarantee of that. And in fact, the data behind the scenes may not even be stored that way. More than likely, it isn't stored that way. The data can be stored in any way, shape, or form, and it's your query that needs to do the ordering if that's a requirement. So remember that behind the scenes, your database could be storing this data in all kinds of manners. It doesn't mean that the data has a certain order. That's more something that you would worry about when it comes to query time. All right, so when we talk about putting together and designing entities, attributes, and relationships, the way we do it is by using a shorthand representation. It's pretty simple to get. You're going to have your table name and then each attribute of the table. Pretty simple. Now, with that being said, oh, and by the way, we're going to build on this a little bit in a moment, but not right now. Remember, table and then parentheses and then all of its attributes. Now let's talk about a functional dependency. If an attribute, such as B, is functionally dependent on another attribute or collection of attributes, let's say A, if a value for A determines a single value of B at any time, then B is functionally dependent on A. To do that, when you want to say that in your notation, this is how you do it. You are saying that A is functionally dependent on B. Excuse me, I said that backwards. And by the way, you're going to get that. That's what's going to happen in your homework. You're going to get it backwards. This actually says B is functionally dependent on A. So A is what derives B, because B is functionally dependent on A. So that's kind of how you kind of read it, is A is driving B, A creates B, or B is cannot live without A. So B is functionally dependent on A. Functionality, another way to read it here is A functionally determines B. Oftentimes you can't determine from sample data what functionality is, where functionality exists. Oftentimes you need to know what's behind the scenes, what the requirements were, any user policy. So be careful when you're looking at data that you don't just jump to conclusions, because sometimes you could be wrong. So functional dependency. Let's take a look at this table. Is there any functional dependency? So in this example, we're talking about functional dependency. Believe it or not, this column cannot exist without this column. And more so, if we want to talk about it, there's very well possibly another table out there that is in regards to pay classes, and the data that you're going to find in this table wouldn't exist without this piece of data. So again, there's that functional dependency. All right, let's talk a little bit about primary keys. Oftentimes, it's a unique identifier for a table, and it's a column that you're going to have. It could be also multiple columns that make up a primary key, but it's unique to the table. You won't see more than one. And it's oftentimes a good way for when you're doing searches for very specific columns, very specific row or rows of data in your database or your table. That's how you're going to use it. So the primary key oftentimes makes your row of data unique. So if you've got an attribute A, so column A, or like I said, it can be a collection of columns, is the primary key for the table if the columns in R are functionally dependent on A. No subcolumn of the columns in A can be a collection of columns and not just a single column. Also has property 1. So if we go back to our example here, it's very unique and understandable to say that 15 represents Raphael. Campos. Now, maybe there is another Rafael Campos in the database. Maybe we've got two. Somehow we found two gentlemen named the same, and we've got them. But this Rafael is represented by 15. This guy at this address is functionally dependent now on this rep number. And because of that, because 15 now represents this piece of information, we can say that 15 is the primary key for that. And in fact, we could really go as far as to write this out. And we can have last name, first name, and then, like I said, the rest of these columns here. So that is our primary key. So database design. When you're given a set of requirements that the database must support, and the requirements gathered through a process known as system analyzing, sorry about that, you have the beginnings of a database design. And there are definitely different methods to do when going through a design method, but this is a really strong 6-step process that a lot of people use. So what we're going to do is we're going to read those requirements, identify the entities. This is an important kind of first step, is what are our nouns? Then we're going to identify the unique identifiers for each entity identified in step 1, aka primary key. Then we're going to define the attributes for all those entities. Step 4, identify the functional dependencies that exist among the attributes. This is how we start to break up the relationships. Oh, that's a horrific way of writing that. And then use the functional dependencies to identify the tables by placing each attribute with the attribute or minimum combination of attributes on which it's functionally dependent. We'll see a little example of that here in a moment. And then identify any relationships between the tables. So let's go ahead and let's just jump into that, because it's an awful lot to say. Oh, did it again. It's an awful lot to say. We can definitely probably understand a little better if we take a look at it. So for the tile distributors, we must store data about sales rep, customers, items, orders, and order lines. Right there, we've got our first set of nouns. Must enforce certain constraints. For example, there is only one customer per order. On a given order, there is at most one line item for a given item. Now, sometimes you're going to have to read between what's being said. So it's saying on a given order, there is at most one line item for a given item. So what they're saying here is you cannot have 0 line items. If there's 0 line items, then the order doesn't exist. But it also is saying at most. So that means there is only going to ever be one item. So you can have 0. Oh, excuse me. Actually, on a given order, there is at most one line item for a given item. So to be honest with you, this reads a little weird. On a given order, there is at most one line item for a given item. What's really being said here, and I've seen this before, it's just a really weird way of saying it, is that there has to be at least one item, but there could be many. And by the way, when we say many, we often represent that with an N. So there is at least one item, but there's more than one item. There can be more than one item. And the quoted price may differ from the actual price. I'll tell you, if I was reading these requirements, I would definitely go back to the customer and ask questions and say, hey, this doesn't make a whole lot of sense. Can you help me out with this? But I'm pretty sure that that's what they're saying in this, is they want at least one item for a given order, which makes sense. You don't have an order unless you have at least an item. All right, so let's apply the requirements to the 6-step design. We're going to identify the existence of, database, apply the requirements to 6 steps in design method. So we kind of started doing that. We did the step 1, which is to identify the entities. And one of the things that we have here is the attributes. And they're not really detailed about the attributes in this database design requirement. But in this, you would start to pick out, okay, well, listen, what is a sales rep? What makes up a customer? What makes up an item? We have some examples previously, but that's how you would start to figure out and get more information from the client. Like, is this what a sales rep is? What makes up a sales rep? Well, it's their name, it's their address, maybe it's their pay grade, all these kind of things. So that, again, that's why it's important to understand and make sure you're getting good requirements. As we go through, we're going to find out what the functional dependencies are, and we're going to use those dependencies to figure out the attributes to help us make up primary keys and then show the relationships. Now let's talk about normalization. In normalization, we identify the existence of potential problems. And when we do that, we then make use of normalization to fix those problems. So the goal is to convert an unnormalized relations table. By the way, good. I'm glad that they threw this in here. Relations is another word for tables. Okay? So always remember that. If you see the word relations, it's a fancy way of saying tables. Just like if you see attributes, it's another way of saying columns. So just kind of keep that in mind. All right. So convert unnormalized relations types that contain repeating groups into various types. So what does a unnormalized table look like? Well, let's again go way back to that one table I was showing you. When you have repeating groups, and please understand this, because this is how and one of the homework assignments is you actually need to create some data that shows data in an unnormalized format. And to achieve that, you're going to have to do this. You're going to have these repeating groups. This is unnormalized. So when you have normalization, when you start to normalize, you technically have 5 layers of normalization. Most people only really talk about the first 3. You don't tend to start talking about the 4th and 5th until you really need to squeeze performance out of your database. And the reason being is there's a little bit of a trade-off with those last 2 levels of normalization. You actually start to split out the data so much that it makes using the database very complicated. So most people stick to the first 3, and this is probably one of the slides in the deck that always make me laugh, because it's pretty self-explanatory. In case you didn't know, 1NF is better than unnormalized. And lo and behold, 2NF is better than 1NF. And surprisingly, 3NF is better than 2NF. I think y'all could have probably figured that out, but it is a slide, and so I covered it. So that first normal form, or 1NF, is to convert an unnormalized relation to 1NF, you have to expand the primary key to include the pk of the repeating group. This effectively eliminates the repeating group from the relation. So, with that being said, when we go back to those example tables that we had, this is the start of 1NF. There's only one thing that's missing from this table to make it 1NF truly and formally. In fact, if you gave this to me as an example of 1NF, I would take it because I would notice that this combined with this could be the primary key. Remember what I was telling you have to be careful when it comes to primary keys and functional keys without fully understanding the relation, the database behind the scenes. Just looking at a table like that, I'd have to assume that this, like I said, this plus this makes up the primary key. Because those two pieces of data put together does show it provides a unique identifier for every single row. So this technically is in 1NF. I would make it more 1NF by having an actual primary key up here. But because of these two columns, they technically have a primary key. All right. Now, don't forget, 2NF is better than 1NF. So this is just an example of what we've been talking about, where we took these repeating groups. Oh, that's not a repeating group. Sorry. Let me erase that. These repeating groups. And we are going to combine or separate them out so each one has its own row. In fact, here's one of the repeating groups broke out. Here's, you can see these two numbers the same. So here's another repeating group broken out. Same thing here. So now this is 1NF. Second normal form. Redundancy causes problems. Update anomalies. So what they're saying is, here's the issues you're going to have with 1NF. You're going to have redundancy problems, and that makes it really difficult to update your data. It provides inconsistent data, and additions and deletions become problematic, right? So that's why typically we want that 2NF. So how do we get 2NF? Well, here is our table. Here's our table. Let's see what we have here. We've got two order numbers here that while we do have these line items broken out, we definitely can see that there's some repeating data. In fact, this is repeating data. And so, again, how do we get this into second normal form? So a relationship is in second normal form if it's in 1NF and no non-key attribute is dependent on only a portion of the primary key, or all non-key attributes are functionally dependent on the entire primary key. So let's see if they've got an example. Oh, this is also another thing. A 1NF relationship with a primary key that is a single field is in 2NF automatically. So what they're saying is, this table, which was in 1NF, can be split out to three tables. We can have a orders table that takes this first two pieces of information. So now we have 51610, which was two lines here. It's now just one line. The item that's now its own table with line item and description. And then finally, we put these pieces of information with these two pieces of information together to create that third table. So these two columns bring, let me erase that. This column references that, and this column references that, and then this is its own unique data to go along with that. So, why did we do all that? It's because, let's go back and look at a bigger version of this table. Now, you're the database administrator, and someone comes and says, hey, I want TR40, instead of saying tic-tac-toe, we want to be funny, and we want to call it tic-tac-toes. Do that thing and make your updates to make tic-tac-toes work out. So I come to this table, this is my table here, and I write a query that updates this to add the S to that. And in this data, fine. Nothing bad happened. Right? But now, let's say, give me 1 second, I gotta find one of these that are repeating. There's gotta be one here. Of course, it doesn't want to pop out at me like it should. All right. Here we go. Nope, even that's problematic. All right, so we're going to just make up one. Let's go back to our tic-tac-toes. Let's say we have another piece of data down here. That's 51699. Same date, and then we're going to say TR40, and we know it's the tic-tac-toe, and just B3, and let's say $62. Okay. Now, again, scenario comes along. One of my coworkers says, hey, we're changing it to tic-tac-toes. And I go in and I make the change, and I say, update the query, and for whatever reason, and believe me, this does happen, the query crashes in the middle of the update. So now row 1 here says tic-tac-toes, but this says tic-tac-toe. So now I have TR40 in two different places with two different descriptions. Can you see the problem that's starting to arise here? Not to mention, every time I sell TR40, am I going to put that as the item number in the description in the table again? At what point does that become redundant? It comes to be a lot of data repeated over and over again. So to clear that up, to make that simple, let's have an items table. Let's have an items table. So this way, the data, the TR40 here, is only in one place at any given time. My updates are going to be simple, and I'm not repeating this data over and over and over again like I am here. I do it once and it's done. This comes back to the same thing kind of over here with the orders, is I don't need to keep having these dates for the same order repeated. 51610 it's on the 25th of October and 2015. Well, I only need that once, and I only need this information once. So here it is, only once. That's where you start to see the 2NF. All right. Clear. Back to my mouse here. So then what is third normal form? Now we're going to, so update anomaly still possible. It's determinant, an attribute or a collection that functionally determines another attribute. So what does that mean? All right, so let's look at this table. We've got a third, this is in second normal form, but not in third normal form. Okay, so this table here, the thing to see, what you're going to notice right away is it's kind of two tables in one. We've got this customer piece, and then we've got this rep piece. Now, at first, when we're designing this, maybe it made sense, right? Maybe we didn't expect to have that many customers. Maybe we thought, you know what, each customer is going to have its own rep. Um, and then at some point, maybe it changed, or maybe we just didn't do a good design. And that's possible too, right? But in this case, what you can quickly see is, man, look at all this repeating data. One of the things you're going to notice with normalization is we're trying to really get rid of repeating data. Whenever you have repeating data, the more times you repeat it, the more likelihood of getting bad data. Like I said, those updates that only update so many of them and then it crashes or what have you, data just can get really corrupt. If you allow your database to have repeating data, you're giving yourself more and more opportune times for your data to become corrupt. So we try to avoid that. And in this case, we want to pull this data out because this is functionally dependent on this, but it's not functionally dependent on this. This data is functionally dependent on this, but not on this. So kind of remember that. That's how we know we've got something going on here is we've got two pieces of data functionally represented by another piece of data that isn't the same. So this to this, this to this. That's our big giveaway that we're not in third normal form. So third normal form is a relationship that is determined if it contains. Excuse me, I'm going to try that again. Relationship is in third normal form if it is in two normal form, and the only determinants it contains are the candidate keys. That's a real fancy way of saying you can't have multiple. Can't have multiple keys like this, representing other pieces of data. It's also called the Boyce-Codd normal form. And the great thing is you should remember. Oh, that's not what I wanted. Nope. All right. Well, I wanted something different, but we're not going to get it. So that is just how it's going to be. This you need to know for your test. Beyond that, I've been in this business for a long time, and I can't remember the last time one of my colleagues, everyone referred to it as that. I would even go as far as I think most people don't even know that. Again, they're going to get back to calling it this 3NF. All right. So what does that look like? It's pretty simple. We're going to do just like we did with the second normal form. We're going to pull the tables out. So you're going to have, this piece of information come here, and this piece of information come here. And there you go. You now took one table, essentially, and you kept on driving it all the way down to third normal form. All right. Now, the last thing for us to talk about in this class is the ERD, the Entity Relationship Diagram. They call it an ER diagram, but most people call it definitely ERD. So, Entity Relationship Diagram. It uses rectangles. Represents the entities. Arrows represent the relationships. We're going to show you several different ways to create an ERD. There are there's plenty of different ways to do it, and when you start using different tools, each tool kind of has its own way of doing it. But for most people that are used to ERDs, we can look at an ERD and pretty quickly understand what you're trying to accomplish. If not, we might ask you to tell us what's going on. But here you can see in this, our squares are our relations, which remember, relations are our tables. So we have a rep and we have a customer and we have an orders, an order line, and an item. In fact, the arrows now show what the relationship is. So here you can see that this relationship is to this, and this relationship is to this. Now, it's saying an arrow represents a one-to-many relationship. What I'll tell you is it's kind of hard in these diagrams to really know that, because an arrow could also represent a one-to-one relationship, and while one-to-ones aren't all that common, they do exist, and so it can happen. And so the most part, and the other thing too is you don't know what this side is, right? So it could be, is this a one to many or is it a zero to many? You don't know. Maybe it's a 0 to 1 to a 1 to many. We're not sure what this arrow represents, but again, for the most part, to someone that's just looking at this and needs to look at it quickly, this does its job. It represents what it's supposed to do. So back to kind of the arrows here. For this sake, we can say that these arrows are representing at least a one-to-many relationship. And the important piece here is to see how this is working. Look at this guy here. We've got this table coming in here and this table coming into here. The fact that we've got one table with two relationships saying that there's a many relationship means that this is stopping a many-to-many relationship. Kind of understand that if we were to get rid of this table, we would have an arrow that goes like this, which means there's an orders to items, means there's many-to-many relationship. And we try to avoid those. So that's exactly what we're doing here is we actually have kind of this table in the middle. Oftentimes these are known as lookup tables. We call them lookup tables because it's a lookup that brings this information together with this information. But that's why we have one table with too many arrows pointing to it. Now this version is known as the crow's foot. And even this is a little bit different than the crow's feet diagram that I like to use. In the ones that I like to use, you would actually have a line here that says that this relationship is a one to many. And I shouldn't do that because nobody ever says M there. It's a one to many, which is an N. One to many. One to many. And so again, on the crow's feet, the version that I'm used to signify the one, you get single line. Let me make sure I'm not jumping ahead here. And let me just look at yeah, I'm not. Okay, good. So the other thing too here is there's other types of representation when it comes to crow's feet. If you see two lines, this means there has to be one and only one item. This says one and only one item to many. This means many. Now, if we have, let's say, a line above the many, like that, this means one to many. That means there has to be at least one item in here for there to, there has to be at least one item for here for every one of these items. Now, that doesn't always happen, and I wouldn't even say that it's common or not common. I'm just saying this representation right here says that there could be a customer item in here, but there's no orders yet for that customer, which is very, very true. You could have a customer without any orders yet. They've called. They're going to be ordering down next week sometime, but we want to get their customer information in. We do that. Some people will say, well, no, they're not a customer. They're not a true customer until they've ordered something. So in that case, we might say that there has to be, there's going to be at least, there's one to every one to many items. That's a really bad N. So there's a one to many items. As in, this is saying they won't even be a customer in our database until they at least have one order. In fact, we can even start to say that customers are functionally dependent on orders because we need to have at least one order for them to be considered a customer. Again, it comes back to the requirements. And that was what we were saying before is functional requirements don't always, functionality doesn't always, aren't, when you're looking at things like this, aren't always common. You can't just see it right away. Sometimes you have to know the actual requirements. So this crow's foot is a second way. And here's a kind of a third way. And again, you've already kind of seen what I've done. This adds a little bit more. So first, we've got our entities. And then we've got our numbering, right? Now we've added a third thing, which is this neat little piece, which describes the relationship. And it only describes the relationship. In fact, maybe when you're looking at the database, maybe they call the relationship because in a database you can actually name the relationships. Maybe they named it that, but they don't have to. That word represents is actually for our benefit. It's there to help us understand that a rep represents a customer, and a customer placed an order. And oh, by the way, key here on this one, I picked it out when I first saw this. Placed, in my mind, says you can't have a customer unless they've placed an order already. Now, if it said places, then I would say that a customer could have existed without orders already. But the fact that they said placed, I would assume that you have to have at least one order before you can become a customer. And by the way, to represent that, the end's correct, but you would say, let me get the right color here. You would say one ... end, stating that you have to have at least one to many, but it can be to many. All right. So back to what we were talking about here. We've got orders, contains, order lines, and then item is on order lines. Now remember, because we always want to read from the one to the end. So the item is on an order line, and here's the one, orders contains order line. Okay. So we did a bunch of stuff. We defined entity. We defined what an attribute is and the relationship and what a relation is. What is a relation? It's a table. Functional dependency, that's that funky little arrow that we talked about. The primary key, which goes kind of hand in hand with functional dependency. We talked about the 6 steps of designing the design method. The hard part is for the homework usually is this normalization. What does it mean to be unnormalized? Your first normal form, your second normal form, and your third normal form. And then we talked about what the ER diagrams or ERD look like. We showed the 3 most popular versions of an ERD, but again, there is a bunch more. So if you've used in your own work different, don't think that we did that on purpose. Again, we just covered really the top three. That is all for this lecture. I know it was a long lecture. I will tell you again, I am going to try to get a video up here as quickly as possible in regards to the homework. So that way, and it's just going to go over a little bit of the homework. I don't want to do all the homework for you. It's to give you an idea of what to look for, what to be doing, how to do it, and use those videos to help you. And make sure you get your work in on time. And I hope everyone has a great week, and we'll talk to you soon.